Alright, in this tutorial, I'm going to show you guys how to perform GBSA calculations and MMPBSA calculations in Ambertools. So starting off, this is assuming that you have Ambertools already installed and the path is set correctly. So we're just going to go into how to actually perform the calculations by making the complex receptor and ligand parameter files, the command to actually run the calculations, and then how to make the input file. So first thing you want to do is this only applies if you made your parameter files, or if you solvated your protein inside of Charm GUI, because when you do that, your parameter file, it has something called CMAP in it, which can affect the overall cancellation of the internal energy terms in the free energy calculations. So the first thing you're going to want to do is to open the parameter file that you used to run the MD simulation with a text editor. Wait for it to completely load. All right, now we're going to want to Control F to find the CMAP terms. Actually, this one right here is the wrong one. I'll do it on the test because I already got rid of the CMAP in that one. So we're going to open up the test parameter file. Now we're going to Control F for CMAP. Wait for it to load. So now it finds these CMAP terms. So from this line right here, the flag CMAP count, you're going to highlight it, and you're going to delete all the way, because all these are still CMAP terms. See flag CMAP parameter, flag CMAP parameters. You're going to go all the way down. These are still CMAP terms. And it keep going. Until you get to here, the flag solvent pointers. So you're going to delete all the CMAP terms up until you get to the percent flag solvent pointers. Just delete like that. Save the parameter file so it no longer has the CMAP terms. Wait for that to completely save. All right, perfect. So now we can open up a terminal here. All right, so now we can move on to the next step of the tutorial. So the first thing I like to use is the ante-MMPBSA Python script. This is used for both MMGBSA and PBSA calculations. So I'm going to copy and paste it here and explain what this stuff means. So first off, we have here the actual command to running using the anti script. So you just write anti-MMPBSA.python. Then you do -p. Here you put your solvated parameter file from MD simulation. Here you're making a complex, a receptor, and a ligand parameter file to be used with inside of the free energy PBSA or GBSA calculation. So these can technically be named anything, but for simplicity's sake, I'm naming it complex, receptor, and ligand parameter files. Next step is you want to strip your water and your ions. So I made these files and ran MD simulations using Charm GUI. So with inside the parameter files, water is named WAT, chlorine is CLA, and potassium is POT. If you're using sodium, you might have Na, or basically different programs use different things to specify their ions. So you want to check your parameter file first to see how they name their water molecule and their ions before you use this command to strip it. So it's dash and then .s, and then you do colon water WAT colon chlorine CLA colon potassium POT. Then you do -n. Here, this is stripping the ligand from your parameter file to make this ligand parameter file here. So you need to specify which residues your ligand is. So for example, in this case, our ligand, we're making it to be the RBD of the SARS-CoV-2 spike protein, and these compromised residues 597 to 789. So you have to make sure you know which residues compromise what in your parameter file before you put random residue numbers here. For example, if you were using a ligand, a lot of times Charmgoy likes to name the ligand like NGT or H4B or whatever it is inside of their inside of the PDB database. So you could put like HB4 NGT depending on what type of ligand it is. And then we're going to specify this command. So we're going to put radii mbondy2, which is the most common radii to use within the calculation. And then we're simply going to just press enter. So as you can see, the first step is stripping the water, potassium, and chlorine from the topology file. And then it's going to make a complex receptor that has nothing but just the protein in it. Could take a little bit of time. Now we're going to create a receptor file. So our receptor file is going to strip what you specified here from the entire complex. So we just have the receptor, which in this case would be ACE2. And then we are going to create just a ligand topology file. So it's going to strip from the complex file just the ligand residues from the complex, and then create a ligand topology file. So now all these, the complex, ligand, and receptor parameter files are now in the folder where we ran these calculations. And also note, this is a solvated parameter file used in MD simulation, which is specified here with the P. And we're also going to need the trajectory production file where MMPBSA calculations are going to be performed from. So now we're going to go to our input file. So I have this pre-created, but if you were starting from scratch, you can do like vi MMPBSA.in to create a new file in Vim, but I already have one, so I'm just gonna open that up. So here we have the input file for running PB and GBSA calculations. So I'm going to delete this and start from scratch. So first you want to do @general. This is going to specify the basics of the calculation. So when I ran the MD simulation, I had 3,000 frames, okay? I wanted to perform the calculations from 45 nanoseconds and to 90 nanoseconds. So halfway between 3,000 frames was 1,500. So I'm going to put a start frame where I want the calculations to start. Start frame equals 1,500, comma, end frame equals 3,000. So that's going to the end of the simulation. And then, comma, interval. This is what frames the calculations are going to be performed on, also known as snapshot. So for example, I have 1,500 frames I'm doing calculations from, 3,000 minus 1,500. So that's 1,500 frames. So if I divide that by 6 interval, I'm going to be performing the calculations on every 6 frame for those 1,500 frames. So I'm going to have 250 frames total where calculations are going to be performed and average across those frames. I want to specify the strip mask because these were stripped from the parameter file. So I want to specify that I stripped water, chlorine, and potassium. And then I want to put this little backslash here. when performing the calculations, I recommend to do GB first and then a second run with PBSA, because GBSA is less computationally costly. So you can run like 200 frames with 20 processors in about 1 hour. But for PBSA, 25 frames would take you like 3 to 4 hours. So if you specified that you wanted to do an interval of 6, you would be calculating 250 frames for both PBSA and GBSA if you put them in the same script. And that would take a very long time. It would take about an hour for GBSA, and then probably like 10 plus hours for PBSA, and that's with 20 plus processors, which most people don't have. So you're going to do backslash. So here first, I'm going to show you how you would run a GBSA calculation. So the only thing is, all you have to do is do @GB. There's a few generalized Born models that you can select. This is basically up to the type of system that you're performing. The most common generalized Born models, which calculates the polar solvation energy or estimates the polar solvation energy, is IGB2 and IGB5. So for most people, 2 and 5 are pretty equivalent. Subsystems, it kind of depends what GB generalized Born model you want to use. I would recommend checking out the Amber tutorial on MMPBSA GBSA calculation and reading more about what specifically you want to accomplish before selecting a model. So for this tutorial, we're going to use IGB=2. That's a model I've used in the past. It's been pretty good. We're going to do comma. So you can also specify the salt concentration. In most cases, the default salt concentration is 0 in the actual calculation. But if you want to specify like 0.15 molar salt concentration, you can put 0.15, comma, another backslash, and that's all you need to do for GBSA. That's literally it. You just save it. This is your input script for running the calculation. Everything else would be as default. So again, if you want to add more parameters to GB and use something other than default, you would have to check out the manual. There's a bunch of default stuff to use, or a bunch of stuff that's not default that you can use. Now if you wanted to run PBSA, I would recommend, like I said before, just deleting the GBSA and running it separately after this has been completed. But I'll just show it on the same script for simplicity's sake. So then this is @GB. So for PB, it's also pretty simple. It's just @PB. I've noticed a few times that I've had to specify, even though these things are default, I still had to specify them or the calculation wouldn't run. It might be like a Python conversion error. So again, istrng in this case, 0.105, that's salt concentration. It's different than the command for GBSA. All these are default. The INP=2 is default. The radiopt =0 is default, and the PB radii is also default values, but I still had to specify this in the past when performing the calculations for it to run. So possible you might have to do the same. So that's what I would do if I wanted to perform PBSA. But for this tutorial, we'll just delete that and I'll show you how to actually run the command. All right. So to run the command, we're gonna, so this is the actual command right here. So the command is MMPBSA.python. This dash capital O overrides any files that were named similarly to this in the past. So if you run GBSA first and then you want to run PBSA, you can use the same input script with the @pb and then your parameters like I said before, but you're really going to want to rename this output file right here, because if you keep it the same as GBSA, you're going to override the results from that. Then you're going to have, so your first step is to do that. Your input file, which is the one we made above with the vi command, is MMPBSA.in. You can name it anything you want. The -o is whatever you want to name the results. Resultsforwild.dat, results for whatever protein you're studying. You could also do .csv if you want an Excel file. -sp, this is your solvated parameter file, the one you used in MD simulation. This is your complex parameter file, the one you made above using the ante-MMPBSA script, which is your receptor parameter file. So it's SP, CP, RP, and then LP, ligand parameter file, in this case, the RBD. And then -y is the production trajectory file. A lot of times it's named .nc for the compressed version. There's a few other versions that you can write out in Amber, but this is your production trajectory file here with y. You just press enter, it loads and checks your parameter files. It's using Sander, so make sure that you have Ambertools installed. It's also going to use CPP Traj. And you're going to prepare the trajectories for simulation here. We're not going to wait for the actual production. I'm just showing how it's starting. So as you can see, we have 251 frames here, which we specified in the input file. We're starting to run the calculations using Amber 18 Sander module, and it's starting by calculating the complex contribution, then I'll do the receptors contribution, and then the ligands contribution, and then the calculation would be done. Like I said before, 250 frames takes about 50 to an hour with a process of 24 CPU cores. So it could take more or less depending on what system you're running it on, but I'm not going to waste time showing you that. So we just interrupted it there. I'm just going to show you what the final results will look like. So this is what results would look like for the calculations. So as you can see, we ran GB using the IGB2 method with salt concentration of 0.15, 1500 frames at an interval of 6. So we calculated using 251 frames. As you can see, it found our receptor mass being residues 1 through 596, ligand 597 to 789, which was the RBD. Calculated, performed using 251 frame. The generalized boron E surface calculated using the LCPO surface area algorithm, and then all units are reported in kilocalorie per mole. So it calculates your total complex energy component, then your receptors energy component, your ligand energy component, and then difference between complex receptor and ligand gives you the overall delta G total, gives you a standard deviation along with the standard error of the mean. So here we got binding affinity of negative 25.37 kilocalories per mole. If there is any errors, it'll tell you around this area above the generalized boron, saying like your energy values didn't cancel out, which tells you something went wrong, because all the energy values between the complex receptor ligand should all be the right differences to calculate the overall delta delta G. I'm not going to save that. And yeah, that's basically how you run MMGBSA or PBSA calculations this simple way. Thank you.